All right. Hey, everyone. So let's go ahead and let's continue with nodal analysis for today. So last time we had a problem that only had current sources. So this time let's do one that only has a voltage source and kind of see what happens. Okay. So we're going to go ahead and follow the same steps. Like I said, this is a programmatic way in order to solve many of these problems. So first step, we're going to go ahead and, of course, assign a reference node. So I'm going to pick a point on this circuit. Now, realistically, you could pick any point and you'll still arrive at the same answers. But let's go ahead and pick a spot that kind of makes sense for this circuit. Since over here is positive and minus, it looks like the lowest voltage point for this circuit seems to be here. So I'm going to pick that as my reference node, or in other words, pick it to define 0 volts for the rest of this circuit solution. Okay, that gets rid of step 1. Step 2, we're going to go ahead and assign all non-reference node voltages. So every point on this circuit that is a different voltage than this reference node, right? So over here, definitely, I have a different voltage. So I'll label this as V1. Also, over here, I definitely have a voltage drop across this 1K, this 2K, and this 3K. I'm going to pick this to be V2. And our last one here seems to be V3. Okay, all along here is 0 volts, all of this V1, all of this V2, and all of this V3. Okay, so that gets rid of our first 2 steps. Our third step, we're going to go ahead and write KCL for each non-reference node. So we're going to go ahead and write a KCL expression for V1, V2, V3. Okay, so let's go ahead and do that. Now, for our first one, V1, what can we say about the voltage at V1? Well, I kind of just gave it away, actually. If you noticed, we don't have to write KCL for V1. We don't have to worry about the current leaving or entering because V1's already given, so that's kind of the nice thing. When you have a voltage source in a nodal analysis problem, it's kind of a freebie. It's a giveaway. So V1, the equation, ends up just being 5 volts. Cool. Okay. So now let's go ahead and let's go on to V2. Now V2, we don't get that luxury, right? V2, we're going to have to express it in terms of currents, write out a KCL equation, and let's see. So for V2, I need to pick some currents, whether they're leaving, entering, and I'm going to try and pick ones that make sense. Now over here I picked this to be 0, so let's just have the current go down. And now for this 1K over here, is the current leaving V2 or entering V2? It doesn't matter, you're going to arrive at the same equation either way. I'm just going to pick it to be leaving. And the same thing for our third one. Okay, now I'll go ahead and label these IA, IB, and IC. Okay, so they're all leaving that node V2. So to write the KCL expression, I'm just going to say IA plus IB plus IC equals 0. They should all cancel out. Okay, so KCL is there. Now we need to go ahead and write out what what IA, IB, and IC are. I'll start with IB because it is going to be the easiest. So what's IB equal to? Well, it's going to be equal to V2, the voltage across the 2K divided by 2K. Okay. Now let's go ahead and do IA. IA is only mildly more difficult, only because we have two voltages. So I'm going to suggest to let the current help you out. Current, we always say, goes from a higher voltage to a lower voltage. And now I can use my polarity to help me out. Plus V2 minus V1. Okay, so that's the voltage drop across the 1K. Now if we go ahead and apply Ohm's law, divide it by 1K, we get the current IA. Okay, so now we can go ahead and plug all of this back into our original KCL expression. Oh, sorry, I forgot one more. We have to do IC. IC, I'll do the same thing. I'll let the current help me out here. Current always goes from higher to lower, plus and minus. So now I can say IC is equal to V2 minus V3. Divide all of that by 3K. And I have my IC current. Okay, now we can go ahead and plug all of this back in. IA is V2 minus V1 divided by 1K plus V2 divided by 2K plus V2 minus V3 divided by 3K. All of that is equal to 0. And we now have our KCL expression. So now we have two of our three equations done. Okay, we have one left. I'll do this one in green. And notice here, we only have two currents involved here. Okay, so I'm going to go ahead and just say both of my currents are leaving. I picked this one to go down because this is 0 volts. V3, I'm assuming, is higher than 0 volts, so the current goes down. And if I make them all that they're leaving and assign IA and IB, now I can go ahead and say for V3, IA plus IB equals 0. Cool. Now I need to go ahead and define my IA and IB. A little more room here. Okay, so I'll go ahead and do IA first. Notice I'll let the current help me out here. Assign my polarity. Current always goes from higher voltage to lower voltage. So now I'll say V3 minus V2. So IA equals V3 minus V2. Now divide that by, well, for IA we're looking at the 3K ohms. So the voltage we just wrote is the voltage drop across 3K, so divide it by 3K. Gives us that current. Cool. Now, the last one we got to do, IB. I'll notice IB, because I picked it going down, the voltage drop across 4K is just V3. So I can just say V3 divided by 4K is equal to IB. Okay, so let's go ahead and plug all of that back in. V3 minus V2 divided by 3K plus, for IB, V3 divided by 4K all of this equal to 0. Okay, so we're left with our three expressions. Notice that we did get V1 already. We found that out right off the bat when we started solving this. V1 was equal to 5 volts. So you can go ahead and plug V1 into both of these equations, and now you're left with two equations and two unknowns. You can solve that with substitution. You can solve it with, you can add up the equations, cancel out one of your terms, and then use substitution. Or you can go ahead and do the matrix by hand, or you can do it on your calculator. So I suggest looking those up. As far as an exam, I will never give an exam that has a problem that has more than 3 equations. So just in case you're wondering, because I know with problems like this, you can totally end up with 4, 5, 6 equations. That's not something you're ever going to see on an exam from me, at least. You're only going to ever have 3 equations max. That goes for mesh analysis as well as nodal analysis. Okay, so once you go ahead and solve the system of equations, you're going to be left with, let me switch colors here. Well, V1 we already knew. Actually, I'll write these up here. V1 equal to 5 volts. V2 equal to 3.04 volts. And V3 equal to 1.74 volts. Okay, so at the end of the day, all we care about is our original circuit and these 3 voltages. So let's go ahead, write it out, and put these voltages in and see what happens in the circuit. Okay, so I'll draw the original circuit here. And we have those voltages that we found. So over here was 5 volts. Over here, 3.04 volts. And over here, V3, 1.74 volts. Cool. Okay, so let's just take a look at the currents over here. Remember, current always goes from higher to lower. So when we're looking at the current going through this 1K, it better be going in this direction, right? Now, if you want to find that out, what the current is, well, first let's figure out the voltage drop across the 1K. Now we have 5 volts on one side, 3.04 volts on the other side. So real easy, it'll just be 5 volts minus 3.04. That gives us 1.96 volts. Okay, so I just did 5 volts minus 3.04 and get the absolute value for the voltage drop across the 1K. Now, if you're having trouble seeing that, again, just let current be your guide, right? Current always goes from a higher voltage to a lower voltage. I'm just looking at the direction of this arrow. At the tail here is positive, at the head it's minus. So again, I could have just said plus 5 volts minus 3.04, and there's a foolproof way to never screw that up. as far as what the voltage drop is across that. So now at this point, if you want to find the current, what that current was, well, we just do 1.96 volts divided by 1K, just doing Ohm's law. And you'll end up with 1.96 milliamps. Cool. Okay. We did call this 0 volts. So if we look at this 2K again, 3.04 is higher than 0, so the current's going down, and the voltage drop across the 2K is just 3.04 volts. And again, that little trick also works here, of course. So current always goes from higher to lower, plus plus 3.04 minus 0 gives us 3.04. Okay, so 3.04 divided by 2K gives us 1.52 milliamps. Okay, let's go ahead and look at this 3K over here. Well, 3.04 volts here, 1.74 volts over there. Goes from higher to lower, so we know the current must be going in that direction. The voltage drop across the 3K must be 3.04 minus 1.74 equals 1.3 volts. 1.3 volts divided by 3K, just using Ohm's law. Gives us 4.3 milliamps. Let me double check one thing. Sorry, I'm off by 0.43 milliamps. Okay, much better. Okay. And for this last one, we have 0 volts down here, 1.74 volts up there, so the current must be going down. And the voltage drop across the 4K is 1.74 volts. So 1.74 volts divided by 4K is going to be 0.435 milliamps. Okay. Ah, I see. Okay. So, notice these two currents are actually the same as they should be, right? Because we don't have any current going off in any one of these directions. This 3K and 4K are in series, so I should get the same value. I just have a little rounding error in here. So this is 0.435 milliamps as well, or we can just do that. Okay. So that takes care of that problem. Okay, so let's do another one. This time we'll have 2 voltage sources. And we're going to go ahead and actually flip these voltages upside down so we can see that we're going to get the right answer no matter what. Okay, so I'll make this 5K, make this 20K, let's make this 1K. This over here, 5 volts, and notice that these are, I guess for lack of a better way of describing it, upside down, right? We're kind of not used to seeing them this way. Now, of course, first thing we're going to do is assign our reference node. Now, again, you can pick your reference node to be anywhere. In this case, I'll go ahead and pick it to be here. Even though that I know that this is higher, this is the plus side of our 12 volt source, this is the plus side of our 5 volt source, we're still going to be able to solve it correctly, even if we pick our ground to be here. Okay, so that's step 1. Step 2, we'll go ahead and assign all of our non-reference node voltages. So up here, V1. This has a different voltage, V2. This has a different voltage, V3. Okay, so that's step 1 and 2. Let's go ahead and write out our equations for each one of these non-reference nodes. V1, actually, let me do this. For V1, V1 is equal to minus 12 volts. See that? Okay. So because this is 0 volts on this side, this must be 12 volts lower than this side, right? So it works both ways. If minus was here and positive was up here, then we would say V1 is equal to 12 volts. But we have the negative side of our voltage source here, so V1 is negative 12. Okay, I'll do the other easy one here, V3. V3 is also equal to negative 5. Okay, so those are the easy ones out of the way. Now let's go ahead and look at V2. V2, I'll switch colors here. And again, I'm not going to think too hard about this for easeability of writing the current going through the 1K. I'll just draw my current to go down so that it's going towards 0 volts. Even though we know that in our final solution, our current's actually going to be going the other way, our real current. Remember, for nodal analysis, we're just picking current directions for the sake of writing the equations. Once we've solved those equations, we don't care about those current directions anymore. Okay, so I picked this to go down. I'll pick this one to go to the left and this one to go to the right. I'll just have them all so that they're leaving. And then I'll label these IA, IB, IC. And now we can go ahead and do our KCL for our node V2. All right, since they're all leaving, IA plus IB plus IC must be equal to 0. Now all we have to do is write out what IA, IB, and IC are. I'll start with the easy one, IB. Since the only voltage involved is V2, it's V2 over 1K. All right, that takes care of IB. Let's do IA. I'll let the current help me out here. Positive here. Current goes from higher to lower. So plus V2 minus V1. divided by 5K. And our last one, I see again, I'll let the current help me out, plus minus, so plus V2 minus V3. All over 20K. All right. So let's go ahead and plug all of those back in. V2 minus V1 divided by 5K plus V2 divided by 1K plus V2 minus V3 divided by 20K. All of that equals 0. And we're done. We have our 3 equations that we need. Okay, now notice with this one we don't even have multiple equations here. We really just have 2 values, V1 and V3. So we can go ahead and plug those into our equation. And solve for that. So all we have to do is solve for V2. If you go ahead and solve for V2, V2 is going to be equal to minus 2.12. Okay, so just plug these two into the equation and solve for V2. You'll get minus 2.12. Okay, so at this point we actually have all of our voltages. So I'll go ahead, rewrite the problem, and just leave it with just our voltages involved. Okay, we had 1K, 5K, and 20K. 5 volts over here, 12 volts over here, and we found our voltages. So at this point we had minus 12 volts. Over here, that's the one we solved for, minus 2.12 volts. And over here, we had minus 5 volts. Cool. Okay, so again, let's go ahead and look at what the current's doing here. Noticed in the previous problem, we listed this as being 0 volts. That's where we placed our reference node. Remember, voltage is always taken between 2 points. So when I say something is 0 volts, it's 0 volts in reference to something. Well, that something is all 3 of these. So notice now we can go ahead and look at our real current, our actual currents. When we were solving previously, the currents we were assigning were just for the sake of solving those equations or writing those equations out. So over here, our real current looks like it's going from 0 to minus 2, right? It always goes from a higher to a lower. Minus 2.12 is lower than 0. So our real current is going up. Same thing over here with this 5K. Minus 12 is lower than minus 2. So our real current is going down like that. And then over here, minus 5 is lower than minus 2.12, so our real current's going there. Alright, that's what our actual current directions are doing. So now let's go ahead and figure out what our voltage drops are. Now, here is, I think, where that trick comes in really handy. Let's just look at this 5K first. Current always goes from a higher voltage to a lower voltage, plus minus 2.12 minus a minus 12. Okay, that's kind of a mouthful, but it's a foolproof way to never get this wrong, right? So we say plus minus 2.12 minus a minus 12. Well, double negative there, so plus 12 volts. That equals the voltage drop. So the voltage drop is 9.88 volts. Right? Okay, so now I have my voltage drop across the 5K, so just divide it by 5K in order to get our current. So 9.88 divided by 5K gives us 1.98, I'm going to round that, 1.98 milliamps. Okay, let's do the same thing for this one over here, our 20K. For our 20K, current always goes from a higher voltage to a lower voltage, right? So plus a minus 2.12 minus a minus 5. So minus 2.12 plus 5 volts. That's our voltage drop across the 20K. And that ends up being 2.88 volts. Okay, so now to figure out the current, 2.88 divided by 20K. 2.88 divided by 20,000 gives us 0.14 milliamps. Cool. Okay, and now for this last one, the same thing over here. Current always goes from a higher to a lower. So plus 0 volts minus minus 2.12. So 2.12 volts is the voltage drop across that 1K. Take 2.12, divide that by 1,000, and we get 2.12 milliamps. Cool. Okay, so as far as the answers for these problems, that's our voltage drop for the 5K, and this was the current. Over here, voltage drop across the 20K, and our current for that one. And for the 1K, 2.12 volts, and there was our current. So even though we picked our ground to be in a different spot than what was truly 0 volts, we still arrive at the same answers, right? And when you even look at this problem, I mean, what is 0 volts here? It doesn't really matter. What really matters is the voltage drop and the current going through each one of these components. Okay, so that takes care of today. Next time we're going to do one more nodal analysis problem before moving on to some other stuff. Actually, that's not the one. We already solved that. Little foreshadowing. That's what we have next. Okay, so we'll go ahead and do that next time. All right, thanks. Take care, everyone. Please take care of yourselves and everyone around you. All right, I will catch you later. Bye.